Hi there! So, in the last video we calculated the gradients of the loss function with respect to the parameters of the last layer. In this video we will complete the calculations and compute the gradients with respect to all of the other layers. So to start with, I want to recap some of the definitions of our neural network, especially in the forward pass. So the big curly L was defined as the loss between y hat and y. Y hat itself was defined as the last activation, AL. Then the activation AL of an arbitrary layer was defined as the application of the function FL to ZL-1. And ZL-1 itself was defined as the matrix multiplication of WL-1. The indices are all the same, so AL-1 plus the bias BL-1. Okay, and this will hopefully help us to understand the formula here that I have prepared. What have I written down here? What we are interested in for this video is the derivative of the loss function with respect to a parameter of an arbitrary layer. Be it the weight or the bias here, it doesn't matter. It works for both. And so now we can unpack this expression one by one. First we had that the curly L here was defined as our loss of y hat and y, as I had written down just a second ago here. Which is why the first term in our chain rule here is that we get the loss with respect to y hat. Then we get y hat, which was AL, which was FL of ZL-1. This is where the ZL-1 comes from. We get it here in the denominator. Then we expand one more step. So we get ZL here and ZL again, as with the formula, was equal to this here. So we can derive it with respect to AL-1. And then this pattern kind of repeats until we arrive at the layer we are interested in. So we differentiate Z with respect to the A that came previously. And then we differentiate A with respect to its previous Z, etc. And so this repeats all the way down until we arrive at the last layer. So this is the last repetition. And once we arrive at L here, at ZL, then we know that ZL is equal to WL times something here. And this is the time where the parameter actually shows up in the definition of Z, which is why we don't need to unpack the notation any further and are left with the final term here. But of course these expressions are long and we don't want to write formulas that are so long, which is why I want to introduce abbreviations right here. So in the last video we have already defined delta L-1, which was defined as the product of these two terms here. And now we continue this definition where delta L-2 here is the product of these four terms, delta L-3 the product of these first six terms. And so at each new index of the deltas we keep multiplying these two factors here to the previous delta in order to get the new delta. And we do this, well, we don't stop at L, this is just for the picture here, but the delta, the definitions of the delta go all the way to the first layer. So delta 0 is the last delta that we will be using. Okay, and with these new definitions we can write out the formulas for all of the derivatives we will be interested in. So the formulas are as follows. First, the original delta, well, this is just the same as we already had, and all of the other deltas we will define them recursively. So if we have an other delta L-1, and notice that the indices of the delta they descend, right? So they get smaller and smaller. So this here, L-1, can be seen as the next delta, which is one layer or one iteration further, and it is defined as the previous delta times and then whatever comes in here. So notice that the index of the Z here is the same as the new delta we want to define. And so we are starting with the previous Z, we take its partial with respect to AL, and then we multiply it with the partial of AL with respect to ZL-1. And now the index of our Z here is the same as the one of our delta. Okay, and now we can also write down the partials of the loss function with respect to any parameter now, because looking at this expression here, we see that it's the same as this entire chain, right? But everything up until here is just contained in this delta L. So all we really need to do is to multiply this with this here in order to get the correct answer here. And the same goes for the bias. So the derivative of the loss with respect to some bias parameter is the same as delta L times the derivative of ZL with respect to that bias parameter. Okay, but in the last video we have already computed this term here in the case where L was equal to L minus 1. But I hope that you'll just believe me if I say that the calculation we didn't really depend on the layer. The calculation looks pretty much the same for all of the other layers, which is why we can just copy our result from the last video, where we had found that this was equal to the ith unit vector multiplied by the jth entry of our AL. And the same goes for the bias here. We can copy the calculation, and this was just the ith unit vector. And once again, this just simplifies to the ith component of delta L times the jth component of AL. And here this is the ith component of delta L. Okay, and once again we want to gather the gradients into a single matrix in order to make the computation in Python easier. But once again, this here is just the outer product of delta of this vector transposed times this vector transposed. So we can write it down like this. And it's the same thing with our bias. It was just the delta L transposed. Okay, and now the only thing that's left to compute are these two terms here, which define our delta recursively. So let's do that. Okay, so let's look at the first term here. And remember that this is a Jacobian matrix. And matrices, we can write them down in terms of their indices. So what I mean by that is that, well, the index I here is made up of the different component functions of Z, whereas the J's are made up of the different variables in our A here. So what we can do is we can write it as the differential of the ith component here of Z with respect to the jth component of AL, and then gather all of these terms in a matrix. And the reason this is useful is because now we can expand the definition of ZL, which was the matrix multiplication of these terms here plus the bias and the ith entry of that vector. And now we can explicitly write down the ith component of this matrix multiplication. So what we are getting is a sum from k equals 1 to dl. So notice that dl is the dimension of the input here, so al, whereas I itself goes from 1 to dl plus 1, which is the dimension of the output of that matrix multiplication. So we have w, the ith row, and the kth column. So we are sweeping through the columns and multiplying each number here with ALK, and then we're adding the ith component of the bias. And all of this we differentiate with respect to AJ. Okay, and now we can once again pull in the differential into the sum, pull it in front of BI, and as in the last video, it's pretty similar. With this index is unequal to that index, then the entire expression just is 0, because these are different variables. But if the index is the same, so if k equals j, then we are taking the derivative of something that looks like the derivative of x times y differentiated with respect to y. So then only x is left, which means that this here is the only thing that's left. And it's only left in the case where I is equal to j. So I can write it down a bit more precisely in mathematical terms. We are using our delta jk, and the differential of this here with respect to that is, well, let me write down the sum once again, is just WLIK. The differential of the bias here is 0. And of course, most of the terms in the sum are 0 because of this delta condition here. When k is equal to j, in that case we get Wij, and in all of the other cases of the sum we get 0. But now the calculation returns us a matrix where every entry of that matrix is the same entry as the entry of W in that same entry. So this is just returning us W. Okay, so that's neat. That's a pretty simple result. Now let's look at the other term, the partial of AL with respect to ZL. So let's write out the definition again. We had FL of ZL minus 1, like this. And we differentiate that with respect to ZL minus 1. And now, in order to continue the calculation, we need to make use of a very important property of our activation functions, which, by the way, is only true for the activation functions which are not this one here. So it's true for all else except the capital L minus 1, which is the property that FL of some input x can also be written down as GL of x1 in the first component, then G of x2 in the second component, etc. until we get G of xn in the last component. And this is not usual, right? An arbitrary definition of a function that goes from Rn to Rn would normally depend on not only x1 but also on all of the other entries of x. The same goes for all of the other terms here. And also we would have different component functions. We would write g1 and gn. But the condition says that the component functions are all the same, and then it also says that the first entry of our result only depends on the first coordinate of x, and the ith only depends on the ith, and the last only on the last. And this is very useful information when taking the derivative, because now imagine taking the derivative of this term here. Then if I take the derivative with respect to x1, then this is just the same as differentiating or taking x prime of x1, right? Because x prime is well defined for a one-dimensional function. However, if I take the derivative with respect to any other parameter, which is not 1, well, since this component function doesn't depend on any other parameter other than x1, this entire expression just goes to 0 if I differentiate it with respect to other parameters. And this is very useful to know, because if I write this down here in index-wise here like this, let me do that 1 second. So if I write it down like this, then this here is the ith component function, which as per the definition here should only depend on the ith component of the variable, which means that when I take the derivative here, only when I and j are equal do we get something, and in all other cases we get 0. So the first thing we notice is that we get a diagonal matrix, because only in the diagonal are the indices I and j the same. So we get a diagonal matrix, and what do we get in the diagonal entries? So the notation that I will use for this is that I will write FL prime of ZL minus 1. And the prime, with that I mean that we take the derivative of the one-dimensional function that f is made of. And since here we are plugging in dl many values, of course we are also getting back dl many values, which we just distribute along the diagonal of the matrix. So this is what I mean by that notation. And so if we put it all together, we get that the next delta L minus 1 is just equal to delta L times W times the diagonal here, as we just defined it. And now let me put this formula amongst all of the others. Okay, so moving these aside, now we have gathered here all of the formulas we would theoretically need in order to compute all of the gradients for a single sample. But now the algorithm we wanted to use was mini-batch gradient descent and not just gradient descent. And this means that we will still need to average all of those gradients in the neural net, or the gradients we calculated here, over many samples. However, as we will see in the next video, instead of computing the forward pass m many times and saving all of these numbers and then taking the average, there is actually a simpler way to do all of this forward passing and averaging with one big matrix multiplication. And how this is done exactly, well, we will look at this in the next video. So then, I hope you enjoyed it and that I see you in the next one. Bye!